So the second part of 9.8 is going to talk about the radius and interval of convergence. So when we took a look at our Maclaurin and our Taylor series, remember what we're doing is we're writing a polynomial for some other type of function. So what the radius and interval of convergence is going to find for us, it's going to find the region of the graphs where the polynomial Taylor and Maclaurin we write actually comes together and merges with those points on that particular function that we're writing the Taylor and Maclaurin for. And I'll show you some examples on the graphing calculator in a few moments. So here are the methods that we're going to use to help us find the radius and the interval of convergence. So there's really three conditions or three situations that can happen. One is that the series only converges for x equals 0. So in other words, it's only going to converge at the center. So first we're going to take a look at the radius and interval convergence for our Maclaurins when the center is at 0. And this is our worst case scenario, where we only have the one point where the two graphs will actually meet. Another scenario that could happen is that the series is going to converge absolutely and hence converges for all real numbers. This is actually your best case scenario, where your interval of convergence will be all real numbers. So in other words, the polynomial exactly matches up to the graph. The series converges absolutely and converges for all x in some finite open interval from -r to r, and diverges if x is less than -r or x is greater than r. At either of these values, r or -r, they may absolutely converge, conditionally converge, or diverge depending on the series. So what's going to happen is we're going to have to test our endpoints and see what's happening at the endpoints. They may converge or diverge or conditionally converge. This is the middle situation. It's not the best and it's not the worst. So again, this theorem states that for a power series, we're dealing again for the first part just centered at x equals 0. So for this reason, the convergence set of a power series in X is called the interval of convergence. In the case where the convergence set is the single value x equals 0, we say that the series has a radius of convergence of 0. So if it's just that worst case scenario, we say the radius of convergence is 0. And if the convergence set is -infinity to infinity, the series has a radius of convergence of infinity. And the case where the convergence set extends between -r and r, we say that we have a radius of convergence, again, -r to r. So just to kind of give you a visual what's happening, if you have a radius of convergence of 0, then the only place of convergence is at the center. And we're going to be doing our ratio test to help us find what's happening with the radius and interval of convergence. So remember, this is my worst case. And since we're using the ratio test, how we're going to know when we have this is when we find the limit as k goes to infinity, this limit is going to be greater than 1 or it's going to be infinity. So that's how you know you're going to have the worst case scenario. If you've got a radius of convergence for all real numbers, then the radius of convergence is infinity. And again, you know this is your best case scenario. This is going to happen when you find the limit as k goes to infinity, and this limit has to be less than 1 to get the best case scenario. If you've got a defined interval, so notice you've got a definite endpoints, the radius of convergence is r. So what happens when we talk about the radius of convergence, it's talking about how far out from the center that the two graphs will merge together. So this is your radius of convergence. So it's from the center to one endpoint. So like I said, this is your middle of the road. And when you do your ratio test, when you find the limit as k goes to infinity, if this limit's equal to 1, that's how you know you have the middle case scenario. Forced possibilities can happen. Like I said, both endpoints may converge at both endpoints. It may diverge at both endpoints. It may converge at one endpoint and diverge at the other. So those are the four cases. If we have this case, what we have to do is we're going to have to check using our series test to see what's happening at the endpoints. So when you find the interval of convergence, the usual procedure for finding the convergence of a power series is to apply the ratio test for absolute convergence. Remember, the ratio test is the limit as k goes to infinity of the absolute value of u sub k plus 1 divided by u sub k. So remember, if this limit is less than 1, it converges for all real. If it's greater than 1 or infinity, it diverges. Remember, if it's equal to 1, you're going to end up with that middle case scenario where we actually are going to have to find what's happening at the endpoints. So let's take a look at an example. So here's an infinite series. Find my interval of convergence and radius of convergence for the power series. So what I'm going to do first of all is I'm going to have to apply my ratio test. So my u sub k is the x to the k. U sub k plus 1 is x to the k plus 1. So now I'm going to go ahead and do my ratio test. So I'm going to find the limit. And again, still the limit is k is going to infinity. The absolute value of u sub k plus 1 is x to the k times x to the first divided by my u sub k, which is x to the k. So now again, remember I'm taking the absolute value. So the limit as k goes to infinity, the x to the k's cancel, I'm left with an x. Now remember, we're trying to find the limit as k goes to infinity, not with x. So when we're doing these limits, what we're going to do is we're going to yank out the absolute value of x and just worry about finding the limit of the remaining expression. In this particular case, it's just going to be 1. So I know the limit as k approaches infinity of this constant is just going to be 1. So that means that I have the middle case scenario. So I don't have a radius convergence of 0. I do not have an interval of convergence of all real numbers. So remember, to converge, the absolute value of x in this particular case has to be less than 1. So we're going to find this conversion again to converge. It has to be less than 1. So I want to find the absolute value of x values that will be less than 1 here. So what this tells me right here, once you have the x by itself, this number right here is my radius of convergence. So if you look at a number line, I know my center is at 0. So my radius of convergence is this number right here. So I know I'm going to go 1 unit out from my center, which is going to be at 1, 1 unit below my center, which will be at negative 1. So here is my radius of convergence. So now what happens is I have to test and see what's happening at the endpoints. So I have to check my endpoints to see if I'm converging or diverging at the endpoint. So to check, I'm going to check x equals 1 first. I'm going to plug 1 just back into my original series for x. So again, I'll have k is equal to 0 to infinity of 1 to the k. So again, I can use my divergence test on this. The limit as k goes to infinity of 1 is equal to 1, and 1 is not equal to 0. So I know at x equals 1 it's going to diverge. So what that means that in my endpoint, I'm not going to include 1 in that interval of convergence. So then to check the other endpoint at x equals negative 1, I'm going to plug negative 1 in for k. So again, k is equal to 0 to infinity of negative 1 to the k. And again, I can apply the alternating series test. I can find the limit as k goes to infinity of 1 is equal to 1, and therefore it diverges by the divergence test. So neither endpoint is going to be included in my interval of convergence. So my radius of convergence is just 1. My interval of convergence, and again, you can write this in interval notation or write it as an inequality in terms of x, is going to be parenthesis -1 to 1. So that's how you find your radius of convergence and interval of convergence. So probably for you, you guys will think this is your worst case scenario because you've got to do this extra work checking the end. Let's take a look at another example. So here I've got x to the k divided by k factorial. So I want to apply my ratio test. My u sub k is x to the k over k factorial. U sub k plus 1 is x to the k plus 1 over k plus 1 factorial. So I'm going to use my ratio test. So I'm going to find the limit as k goes to infinity. U sub k plus 1, so that's my x to the k times x to the first, divided by k plus 1 times k factorial, divide by u sub k, so I'm going to multiply by k factorial over x to the k. I can cross out the k factorial, cross out that x to the k. So I have the limit as k goes to infinity of x divided by k plus 1. So now, like I did before, we're concerning ourselves with finding the limit as k goes to infinity. So I'm going to pull out the absolute value of x and write this as the limit as k goes to infinity of 1 over k plus 1, which I know is approaching 0. So 0 is less than 1. So this is actually my best case scenario. So again, at my center, 0, I've got an interval of convergence going from -infinity to infinity. So 0 less than 1 is where it's going to converge. So my radius of convergence then is infinity. My interval of convergence is going to be all real numbers. So like I said, after you do your ratio test, if you end up with a limit less than 1, then this is your best case scenario. Let's take a look at C. So k factorial times x to the k. So my u sub k is k factorial times x to the k. U sub k plus 1 is equal to k plus 1 factorial times x to the k plus 1. So I'm going to use my ratio test. The limit as k goes to infinity, my u sub k plus 1 is k plus 1 times k factorial times x to the k times x to the first, divided by my u sub k, which is k factorial times x to the k. So I can cross out my x to the k, cross out my k factorial. Again, I can pull out that absolute value of x times the limit as k goes to infinity. So I'm left with a k plus 1. So the limit of as k goes to infinity of k plus 1 is approaching infinity. And we know infinity is greater than 0. So remember, if you get a limit greater than 0 or infinity, this is going to be your worst case scenario. Your interval of convergence is 0. The radius of convergence is 0. So again, what's happening on the number line, we have my center at 0. The only place that this is converging is at the center. So that's how you know that you're going to have an interval of convergence or radius of convergence. Again, if this is infinity or greater than 1 when you do that limit. So now let's take a look at D. So we end up with u sub k is the -1 to the k, x to the k, over 3 to the k times k plus 1. U sub k plus 1 is -1 to the k plus 1, x to the k plus 1, over 3 to the k plus 1 times k plus 2. Now remember, you were finding the limit as k goes to infinity of the absolute value of u sub k plus 1 divided by u sub k. So then I'm going to find the limit. I'm going to drop those alternators. The limit as k goes to infinity. U sub k plus 1 is that x to the k times x to the first over 3 to the k times 3 to the first times k plus 2, divided by u sub k, which is going to be my x, I have to do the reciprocal, so that's going to be 3 to the k, k plus 1, divided by x to the k. So I can cross cancel. I got rid of the x to the k, I got rid of that 3 to the k. So now I'm going to find the limit. As k goes to infinity, I'm left with x in the numerator times a k plus 1 over 3 times k plus 2. So now, when you find the limit as k goes to infinity, and this is really important, what you're going to take out besides the x, you want to pull out any constants. So I'm going to rewrite this as the absolute value of x over 3 times the limit of k plus 1 over k plus 2, which this limit is equal to 1. So to converge then, I'm going to take the absolute value of x over 3 and make it less than 1. So this is that middle of the road scenario. So now to find what the radius of convergence is going to be, we're going to have to get x by itself. So I'm going to have to multiply both sides by 3. So the absolute value of x is less than 3. So then this 3 is my radius of convergence. So on the number line, if you think about what's happening, my center is at 0. So my radius of convergence is going to go 3 units above my center, which is at 3, and 3 units below, which is at negative 3. So just like I did in the previous example, we have to check to see what's happening at those endpoints to see if it's converging or diverging. So let me go ahead and check 3 first. Again, I'm going to have to plug 3 back into my original series for x. Anywhere I see an x, I'm going to plug in a 3. So I'll have my series k is equal to 0 to infinity, negative 1 to the k, 3 to the k, over 3 to the k times k plus 1. So notice the 3 to the k's are going to cancel. So I'm left with the series k is equal to 0 to infinity, negative 1 to the k, over k plus 1. So then I have an alternating series, so I can apply my alternating series test. So I want to find the limit as k goes to infinity. Again, I'm going to take the absolute value of this, strip the alternator, 1 over k plus 1 is equal to 0. So I know it's going to converge at x equals 3. So that means I'm going to include 3 in my interval of convergence. Now I have to check negative 3. So I have k is equal to 0 to infinity. Again, I have my negative 1 to the k. I have negative 3 to the k, all over 3 to the k times k plus 1. Now another way I could write this negative 3 to the k would be k is equal to 0 to infinity of negative 1 to the k, negative 1 to the k times 3 to the k, all over 3 to the k times k plus 1. So the 3 to the k's cancel, and a negative times a negative, no matter what's going to be a positive. So what I'm left with is I'm left with the series k is equal to 0 to infinity of 1 over k plus 1. So I can use my polynomial test. This is a polynomial. So the degree of the numerator is 0. So 0, and again I'm comparing it with the degree of the denominator, 1 plus 1. I know 0 is less than or equal to 1 plus 1, so I know that this is going to diverge. Excuse me, I should write 0 plus 1. It's the degree of the numerator plus 1 is less than or equal to the degree of the denominator, which is 1. So I know it diverges at x equals negative 3. So I know that I'm not going to include negative 3 in that interval of convergence. So then my radius of convergence, so the radius of convergence is, remember, 3. The interval of convergence is going to be parenthesis negative 3 to 3 with a bracket. So that's an example of when you have one endpoint doing one thing and the other one's doing another. So you also can do these if you're dealing with your Taylor where the center is not at 0, 0. So again, here's my x minus x sub 0, and again, here's my center not at x equals 0. So again, we still have a power series in x. And again, we're still going to have to do the same process like we did for the Maclaurin. You're still going to have your 3 situations we're checking for. It may just converge at the center. And this is your worst case scenario. It may converge for all real values. And this is your best case scenario. Converges over some finite open interval, which would be x sub 0 minus r, comma, x plus r, and diverges outside that particular interval. At either of the values, the series may absolutely converge, conditionally converge, or diverge. So again, just like at the other if we have that interval, then we call this the interval of convergence. Again, if it's where the converges to a single value at the center, we say that the radius of convergence is 0, just like with the Maclaurens. And if it converges for the entire number line and it's infinite, we say that the radius of convergence is infinity. And again, if the interval extends between x sub 0 minus r, x sub 0 plus r, we say it has a radius of convergence of r. Again, the only difference between what we were doing on the last couple examples versus here, your center is no longer at 0. You're going to have some other center. But you still have your worst, best case in the middle of the road. Again, this is your worst case scenario when the radius of convergence is just 0. It's just converging at the center. If it converges for the entire number line for all real numbers, we say the radius of convergence is infinity, and this is your best case scenario. Or it may converge at some finite interval. Again, you still have to test the endpoints to see what's happening. This particular case, we say that the radius of convergence is r. We're still going to use the ratio test and have to use possibly our other tests to check the endpoints if needed. So always know where your center is. So if you take a look at this particular series, whatever number is being added or subtracted to x, that's going to tell you what your center is. So in this particular case, my center is at x equals 5. So I still have to use my ratio test. So my u sub k is x minus 5 to the k. My u sub k plus 1 is going to be x minus 5 to the k plus 1. So I will still want to find the limit as k approaches infinity of the absolute value. So then u sub k plus 1 is x minus 5 to the k times x minus 5 all over u sub k, which is x minus 5 to the k. So x minus 5 to the k cancels. Now, just like we did with the other examples when the center was at 0, I want to find the limit as k approaches infinity. So what I'm going to do is use my limit property. I'm going to rewrite this as the absolute value of x minus 5 times the limit as k goes to infinity, and all I'm left with is a 1. So this limit's going to be 1. So now, to converge, I know that the absolute value of x minus 5 has to be less than 1. Once you isolate the absolute value on the one side, just like we did in the Maclaurens, this value right here is your radius of convergence. So now, since my center is at 5, the only difference from what I did with Maclaurin versus these is my center is at 5. So then the radius of convergence is going to be 1 unit greater than 5, which will put me at 6. 1 unit less than the center will put me down here at 4. So the endpoints I have to check in this particular case are going to be at 4 and 6. Because again, here's my center at 5. This is my radius of convergence. So let me check 4. So to check to see if it's going to converge or diverge at the x value of 4, just like I did for my Maclaurens, I'm going to plug 4 back into my original series for x. So k is equal to 1 to infinity of 4 minus 5 to the k over k squared. So I end up with a negative 1 to the k over k squared. So I can use my alternating series test. The limit as k goes to infinity of 1 over k squared is equal to 0. So I know it's going to converge at x equals 4. So I'm going to include 4 in the interval of convergence. So now I have to check 6. So it's going to be k is equal to 1 to infinity. 6 minus 5 to the k over k squared. So that's going to be 1 over k squared. So the test we can use on this is a p-series. So since 2 is greater than 1, I know that this is going to converge. So it converges at x equals 6 as well. So then my radius of convergence is equal to 1. My interval of convergence is going to go from bracket 4, comma 6. So if you have you still do the same process even if the center is not at 0, 0. So here's another one. So we have 3x plus 2 to the k over 2 raised to the 2k. So I still have to use my ratio test. So now this one, the center is going to be a little bit trickier to identify. So what you have to do to identify the center is imagine factoring out the 3. So again, if I have 3 parentheses x plus 2/3. So the center is going to be at negative 2/3. So if that coefficient of x isn't equal to 1, or you just find the 0, set it equal to 0. So my center is at negative 2/3. So again, I have to use my ratio test. So it's going to be 3x plus 2 to the k over 2 raised to the 2k. U sub k plus 1 is going to be equal to 3x plus 2 raised to the k plus 1 over 2 raised to the 2. Now be careful, that's 2 parentheses k plus 1. So if I distribute that, that's going to be 2 raised to the 2k plus 2. So now I'm going to use my ratio test, the limit. As k goes to infinity, my u sub k plus 1 is a 3x plus 2 to the k times 3x plus 2 to the first, all over 2 squared times 2 to the 2k, divided by my u sub k, so there's my 2 to the 2k, over 3x plus 2 to the k. So again, I cross out that 2 to the 2k, 3x plus 2 to the k. So I'm left with the limit as k goes to infinity of 3x plus 2 all over 4. So just like I did, again, I want the limit as k goes to infinity. I'm going to bring out the factor with the x as well as the constant. So the absolute value of 3x plus 2 over 4 times the limit as k goes to infinity of 1, which is equal to 1. So I'm going to have that middle of the road scenario. So now remember, to converge, this has to be less than 1. So I have to take the absolute value of 3x plus 2 over 4, make it less than 1. So now the first thing I want to do is I want to start preparing this to identify. I want to start isolating what's inside this absolute value. So I'm going to multiply both sides by 4. So the absolute value of 3x plus 2 is less than 4. Again, I need to get this coefficient of x to be a positive 1, so I'm going to divide a 3 out of this. So I have 3 times the absolute value of x plus 2/3 is less than 4. Get the absolute value by itself in order to identify the radius of convergence. So I'm going to have to divide by 3. So the absolute value of x plus 2/3 is less than 4/3. As I've already mentioned, the center is at negative 2/3. This is your interval, this is your radius of convergence. So my center is at negative 2/3. My radius of convergence is 4/3. So if I take negative 2/3 and add 4/3 to it, that's going to give me a 2/3 right here. So there's one of my endpoints for the interval. Negative 2/3 minus 4/3 is negative 6/3, which is negative 2. Again, so this is my radius of convergence. So again, I have to check these endpoints. So to check negative 2, I have to take negative 2, plug it back into my original series for x. So it's going to be k is equal to 1 to infinity. So 3 times negative 2 is negative 6. Negative 6 plus 2 is a negative 4 to the k. Over 2 squared over 2 raised to the 2k. So now remember, another way I could write this with the alternator would be a negative 1 to the k, 2 squared to the k all over 2 raised to the 2k. So that 2 to the 2k is going to cancel out. So by my divergence test, the limit as k goes to infinity of -1 to the k, it's going to oscillate, so it's going to diverge. So I'm not going to include -2 in that interval of convergence. So now I also need to check 2/3. So when I check 2/3, I'm just going to get a separate sheet of paper so I don't squish it. So to check, x equals 2/3. Again, I'm going to take 2/3 and plug it back into my original series. 3 times 2/3, excuse me, is going to give me a 2. 2 plus 2 is a 4. So I'll have a 4 to the k in the numerator all over a 2 raised to the 2k. Again, another way I could write that for k is k is equal to 1 to infinity of 2 squared raised to the k all over 2 to the 2k. So I'm left with a 1. So then by my divergence test, I can find the limit as k goes to infinity of 1, which is just going to be 1. So it is going to diverge. So I'm also not going to include 2/3 in my interval of convergence. So then my interval of convergence is going to be parentheses -2 to 2/3. The raise of convergence was 4/3. So for this particular case, I usually wait till I get down here to really identify what the center is, even though you can still do it in the beginning, but usually I just wait down here until I get, again, you need this center to have a coefficient of x to be a +1 in order to identify that center. So now, there are the Taylor-Maclaurin series are special examples. Since a power series have variables that can be viewed as a function of x, these Maclaurin series with the interval convergence are the ones you really need to memorize because they do occur most frequently. And again, they're used to approximate those other functions. So e to the x, remember, has your series x to the k over k factorial. So 1 plus x squared over 2 factorial plus x to the third over 3 factorial plus ... The interval of convergence for e to the x is going to be all real numbers. And if you look on your calculator, let's take a look at how well this Maclaurin series polynomial will graph as close to e to the x. So if you take a look at your graphing calculator, I'm going to go ahead and graph my e to the x. There we are. So now I'm going to just type in out to these 3 terms. So 1 plus x squared divided by 2. Remember your factorial sign, you go under math, PRB option 4, plus x to the third divided by 3 factorial. The more polynomials you put in here, the better you'll see that interval of convergence. Oops, I hit the wrong button. Hit delete. 3, math, 4. And I'm going to darken this so you can see the comparison of the 2 graphs. So I'm just going to darken. So here's my graph. Oh, I need to fix my window. Well, there's a graph of e to the x. And there you can see my graph of the Maclaurin polynomial. But if I add on more, plus x to the fourth, the higher degree you take this out, the better it will match. I'll do one more. So there's my e to the x. So now you can see how much closer by me adding on 2 more. And if I add on more and more, you will see that they merge even closer together to get that interval of convergence for all real numbers. Sine of x, remember, has your -1 to the k, x to the 2k plus 1, all over 2k plus 1 factorial. And remember, this series is your x minus x to the third over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus dot, dot, dot. The interval convergence for this polynomial is also going to be all real numbers. Cosine, remember, you only have the even powers. This is going to be a negative 1 to the k, x to the 2k over 2k factorial. So this is going to be a 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus dot, dot, dot. The interval convergence for cosine of x is also going to be all real numbers. The 1 over 1 minus x, k equals 0 to infinity. This is your x to the k. 1 plus x squared plus x to the 3rd plus x to the 4th plus dot, dot, dot. This one does not have an interval convergence of all real numbers. This one is just going to go from negative 1 to 1. And that's the second part of 9.8.